Loving, speaking on mapping class groups. Take it away, Marissa.
Awesome. Thanks for that introduction, Sammy, and thanks to organizers for putting together this online summer school. So yeah, today I'm going to be telling you about the mapping class group. My aim is for this to be a really accessible set of lectures. So we're going to just start with some basics. I really like that Federico had like the list of resources, so I added some as well. So the number one resource for learning about the mapping class group is a primer on mapping class groups by Benson Farb and Dan Margulies. Another resource I think would be helpful is Sol Schleimer has some online notes. It's called just Notes on the Complex of Curves. And then something that I'll be drawing on probably more in the next lecture than this one is Masur-Minsky's kind of very well-known and big results on the geometry of the complex of curves. So this is a set of 2 papers. They're not things that you need to read to understand this at all, but they're references if you want to dive in deeper. Okay, so just to get us started, what is kind of the main topological object that I study? Well, it's just surfaces. So of course we have our familiar sphere. We have our lovely donut. We have surfaces of higher genus. So these holes are what I call the genus of my surface. And of course, we can think of things with boundaries or punctures. So one that I like a lot is the pair of pants, right? This is a 3-hole sphere. I tend to conflate a lot when I'm talking like between boundary components and punctures. It matters sometimes because you can twist around boundaries and you can't really twist around punctures. But when I'm not distinguishing between them, it shouldn't matter too much. Okay, so these are the types of things I want to think about. And one of the most important things that allows us to actually study these is the classification of surfaces. So this is a result that says that a connected orientable surface of finite type. So this is an important distinction. So when I say finite type, I want to consider surfaces that have a finite amount of genus or punctures or boundary components. So up to homeomorphism. So yeah, basically everything I'm going to be considering is up to homeomorphism a finite type up to homeomorphism is determined by the things I just highlighted, right? So by its genus, the number of holes it has, by the number of punctures, and by the number of boundary components. So really there's just these 3 numbers that parameterize this space of surfaces that I'm going to be considering, boundary components. Okay, so this is good, and this allows me to set some clear notation. Maybe I actually will do it here so I don't need to change the page quite yet. So throughout the talk, I'm just going to let SGN be a surface of genus G with n punctures. Okay, and most of the time throughout the talk, I'm going to be focusing on surfaces that have negative Euler characteristic. And just to remind us what that is, for a surface of genus G with n punctures, this is just computed using this formula. So really I want to focus on like punctured tori or higher genus surfaces with genus at least 2, or spheres that have like maybe 4 more punctures. Okay, so great, let's skip ahead. So I'm going to talk about the mapping class group. And so I'm going to start by just giving a very like hand-wavy notion of what the mapping class group is. And so that hand-wavy notion is that the mapping class group is the collection of symmetries of a surface. Okay, so that is pretty floppy. So I'm going to tell you what I mean when I say a symmetry of a surface. What I mean is I'm going to mean various maps of my surface, various homeomorphisms. One of like the kind of simplest examples of this would be like a rigid rotation in space. So for example, here I have this genus 3 surface, which I've laid out very symmetrically. And so one of the symmetries of this surface would be if I just rotate it by 2 pi over 3. Right, so this is like a very nice symmetry. You can see that there's some nice things happening. So for example, if you look at like these curves here, kind of on the handles, you'll notice that this rotation preserves this collection of curves. That's a thing that happens. So this is a type of rotation that we can look at. We could also look at something a little bit more complicated in some sense, but it's again just a rotation. So now instead of just looking at like a rotation like here, like on our surface, we'll kind of cut our surface open into a polygon. So here we have a square, and we have the opposite edges identified as like kind of marked with the color. So this glues up to be a torus. And so now we can think of a rotation of this torus as just being a rotation of this square upstairs by pi over 2. And so the reason I highlight, again, I have one over here, this rotation. The reason I highlight this is a type of rotation where I don't have any fixed curves or fixed collection of curves. So it's sort of different style of flavor of rotation than the one we looked at last. But yeah, these are these nice symmetries of our surface, these homeomorphisms. And then there's my favorite kind. And so my favorite kind of surface homeomorphism is something called a Dane twist. And the way that you can think of a Dane twist is it's something that happens in our surface, but it's happening locally. So really, I want to say like a Dane twist about a simple closed curve. Let's name it alpha. So here, by simple, I just mean that my curve doesn't have any self-intersections. So let me draw just a local picture of this. So here's my annulus, and here's my simple closed curve alpha. And so a twist about alpha, what I'm going to do is I'm just going to cut my surface open along alpha, twist by 360 degrees, and glue it back together. And so that doesn't really look like much if you don't have any other curve kind of marking what this action is doing. So let's take a blue curve and let's do this twist. Now I'm gonna note this twist by alpha. And so what does it do? Again, my red curve stays fixed, right? I cut open and then I glued right back. So my curve alpha stays fixed. But now my blue curve beta, or maybe I didn't name it, but you could call it beta, it just gets twisted around and comes back. So this is the image of my Dane twist. And so this you can see in our surface. Here I have my curves. You can see why I was calling them alpha and beta. You have my curve alpha, my curve beta, and then you can see what happens, the image of beta under alpha, right? It kind of looks the same everywhere, except you see that twisting building up in that annulus around alpha. Okay. So these are all examples of homeomorphisms on my surface. And then I would be remiss if I talked about homeomorphisms of the surface and didn't talk just for a moment about point pushing, because this is what I spent a lot of my PhD days thinking about. So point pushing is another really nice homeomorphism of our surface. So let's take a curve. Let's also call this alpha. And then we're going to take some other curve, beta. So let's take this curve. I'll call this curve beta. And so we can consider the push of alpha along beta. So I'll denote this like this. And so what we need for this to happen is we need some mark point on our surface. And what we're going to do is we're going to think of just putting our finger down onto this mark point, put our finger down to this mark point, and then just dragging along our curve beta and coming back. And we're going to see how that drag kind of pulls alpha along with it. So let me actually draw this. So I'm going to draw the image of alpha in purple. we're just gonna drag. So we drag alpha along, just follow exactly along beta until we come back to where we started pushing. Okay, and so this purple curve, so this really should be in purple. This is the image of our push map. And so even though this looks kind of fancy and cool, it turns out that this is really the same as doing twisting. Along beta and beta prime, where beta prime is if you took, let me draw, can I like zoom? So this is my first time giving a talk on this, so we'll like on an iPad, so we'll see if I can manage this technology. So I could do this. I could think of like putting my mock point here and then taking kind of 2 copies of beta. Oh, what happened? One on one side of my mock point and one on the other side. And so I could call one of those beta and the other one of those beta prime. And then this pushing, is this making sense? Then this pushing is just a twist along beta and an inverse twist along beta prime of alpha. So this is somehow like secretly, this point pushing is just secret twisting. Okay. So these are all examples of the type of things that I'm talking about when I'm talking about symmetries of my surface. And so now that we've kind of talked about the kind of objects we're thinking about, I want to give a formal definition for what I mean when I talk about the mapping class group. So, okay, so like let S. Okay. Again, we'll just have S as be a connected, oriented, finite type surface. And we'll define its mapping class, which I'll denote map of S. This is going to be the group of orientation preserving homeomorphisms of my surface up to homotopy.
Marissa, there's a question. Are the curves alpha and its image under the point pushing map homotopy equivalent?
So so that's a great point. So if you think of this, if you forget about the mock point, then they are homotopic on your surface. So this is like a really good thing to think about. One thing that people think about often is you can think about a map from, for example, a surface with one puncture, like a homomorphism between these mapping class groups, like this. And so the kernel of this, so like call this F, the kernel F, this is the set of these point pushing maps. So these are the things that become homotopically trivial when you forget about the puncture. Yeah, great point. But like punctures, mock points, again, I'm not distinguishing between them. So you could think of it as a puncture or a mock point, that either is fine. Any other questions about this? Okay, one thing to note is that here, since I'm defining this for a surface with punctures, when I talk about the orientation preserving homeomorphisms, I want it to be the ones that fix the collectors of, fix like setwise the collection of punctures, right? They preserve the punctures. Okay, so this is my definition of the mapping class group. And I could not talk about the mapping class group without talking about the Nielsen-Thurston classification. So I've already kind of, without saying too much, I've hinted a little bit about this before, and we're not going to get into it too much. This is the basis for so much of the math I do that I just have to mention it. And so this is a really powerful result of Nielsen, and then Thurston came along and kind of finished everything up. That says that there is essentially just 3 types of elements in the mapping class group. We have finite order ones. So these were ones that I illustrated, right, as these rotations. So you kind of see we have finite order and we have reducible, and there's a bit of overlap. And so the distinction here is that reducible ones are the ones that fix some collection of curves on our surface. So for example, like the Dane twist, they fix the curve that you were twisting about. Or like that very first rotation that we talked about, how it fixed those 3 curves that were kind of on the handles. And then we have these finite order ones, so that some power is just homotopic to the identity, which don't fix any curves, right? So these are like our finite order irreducible, and these are our, here's a finite order and reducible, and here's an infinite order reducible, right? So if you keep twisting around this Dane twist, you're gonna get like a copy of Z, right? You're never gonna come back to yourself. And then in the complement of this, so the infinite order and irreducible elements, these are something called pseudo-Anosov. And so I'll just give like, I'm just gonna say these words. This is not super important for the rest of the talk, but these are near and dear to my heart, so I just wanted to mention them. So these are kind of the most dynamically interesting elements in the mapping class group. And so these are the ones that have this kind of underlying pair of transverse singular measured foliations living on our surface, and they preserve this pair of foliations, and they have a really nice action on them. They have one that they act on by like stretching, and the other which they act on by squeezing. And they do this by this factor, which I denote lambda with F, which is called the stretch factor. And so the reason that I had to mention this is because my entire thesis studies the least dilatation of the stretch factor of pseudo-Anosovs in a certain subgroup of the mapping class group. But yeah, so these are interesting things, but we don't need to spend too much time on the definition. I do want to give just examples, because I've given examples of every other type of element in the mapping class group. So I just want to give 2 examples of pseudo-Anosov elements. And so these are 2 examples. And what is the example? So right now I just have 2 pictures of surfaces with curves. So how do you get maps from these? We're going to do it the same way that we've been doing before, which is by twisting. And so here, the pseudo-Anosov that I mean when I draw this picture is, I mean, you take a Dane twist about your curves alpha, right? So we take a product of these Dane twists, and then we take the product of the Dane twists about my beta curves, and we just take these inverses. So this is a pseudo-Anosov. As I said, these are sort of the most like dynamically interesting, and you can see at least morally why these are, because you see that that somehow there's an action happening on my surface that's happening everywhere. There's kind of this mixing happening everywhere. And so in some sense, that's my justification for saying that. And then the same thing here, we take this, this is my pseudo-Anosov here. It's just a twist about my curve A and an inverse twist about my curve B. And so I won't get into this too much, but I just wanted to give an advertisement, because I do have office hours later this week, that if you're interested in how you can build pseudo-Anosovs, both of these examples that I've just given are examples of Thurston's construction, which is like a really nice construction of pseudo-Anosov. It's very combinatorial. So like, feel free to chat with me about that in the office hours later this week. Okay, I just had to advertise. I couldn't not say this. Okay, but
sorry, there's a question. Do you need those inverses on the beta twists for it to be pseudo-Anosov?
Yes. So there are some examples where you can have like positive powers on both twists, but typically you're going to need to have high positive powers if you're using Thurston's construction, because otherwise you don't get the right property for like the corresponding matrix that you look at. Yeah. Yes, good advertisement for your Bond's work. You can also look at Penner's construction, which is a somewhat more complicated construction of pseudo-Anosovs, where you get to kind of have more choice about like what the powers on your things look like. Okay, awesome. So we've talked a bit about curves on surfaces. And so now we're going to kind of change gears into what most of the rest of this lecture and tomorrow's lecture is going to be, which is a somewhat combinatorial approach, which is, I'm going to introduce the curve graph. So the curve graph is this really wonderful object. And the definition is pretty straightforward. I'm going to take as my set of vertices just homotopy classes of simple closed curves. So again, a reminder, these simple just means that I don't want curves that self-intersect. And one thing that I didn't write here that really should be here is that I really want these to be essential. And that just means that I don't want them to be boundary parallel. I don't want them to be homotopic into a boundary. And I don't want them to bound like a once punctured disk, which means I don't want them to be homotopic into a puncture. I want these to be essential, simple, closed curves. And then I'm going to introduce edges wherever my curves can be realized disjointly on my surface. Okay, so for example, I drew this picture. I have this collection of 4 curves, and these are all simple curves. They're all essential. And now so here I have my red curve. I'm going to connect my red. Oh, I should not use that. I should use my highlighter. I'm going to use my red curve, connect my red curve to my blue curve, because on the surface they're realized disjointly, right? Here's my blue curve, here's my red curve. And then I'm doing the same thing. So green is disjoint from both red and both blue and red. So we connect them with edges. Pink intersects both green and red. So we don't see an edge there, but we do see an edge with blue because these ones are disjoint. Okay, so this is just pointing out, this is just a very small example of this. In reality, the curve graph is locally infinite. So every vertex has infinitely many vertices adjacent to it. So this picture this is just the tiniest sample, just to kind of illustrate the way that we put edges in. This is not all representative of what the curve graph looks like. Okay, so I said curve graph here though, but if you remember my abstract or like my first slide, I said that I was going to talk about the curve complex. And a one complex is good and all, but actually you can also add like higher dimensional faces. So the way that we do that, to think of this as being an actual like simplicial complex with higher dimensional faces, is we'll add a k-simplex whenever there are k plus 1 disjoint vertices. Disjoint vertices. So for example, in this picture, I could add in a simplex in there for my 3 disjoint vertices. Okay. So here I wrote down, here, I'll write this back. So I've been trying to put together exercises for this, but I've been very tardy and haven't. So one exercise I thought of just before this started is the following fact, and I think this could be a good exercise, is that the curve complex is Qi to its 1 skeleton. Okay, so this is fact. You can have this as an exercise. So here, I guess I should say what I mean by this. What do I mean by Qi? So here, this is quasi-isometric. And so that just means it's isometric up to some fudge factors. And that's going to be up to an additive and multiplicative constant. Okay. Okay, so this is great and all, but this is not, what I have told you so far isn't quite true. This doesn't cover all the types of surfaces that I said we'd be talking about in this talk. And so there are a couple of exceptional cases. I wasn't sure if I was going to chat about these, but then after Riley's talk, I was like, yes, I need to, and you'll see why in a moment. So one of the cases that hasn't been covered by the definition I've given so far is the once punctured or like one-hole torus. Another one would be the 4 times punctured sphere, as well as the pair panes, the 3 times punctured sphere. And so here I won't say too much. I just want to point out, right, that here there are no curves which can be realized disjointly, right? The only curve here that can be realized disjointly would be like this boundary peripheral one, right? So here what I want to, right? So like here we have these 2 curves. They intersect once. Here we have the kind of same problem. Any of the essential curves on our surface are forced to intersect. And so I'm just going to do like the easy thing, which is just replace disjointness with what we really mean, right? What we meant before as well, which is we just need minimal intersection. Minimal number of intersections. And so it turns out that the curve complexes for these two, for the once punctured torus and the four-hole sphere, this is the fairy graph, or the fairy diagram, which Riley talked about, right? So this is kind of a cool fact. This pops up all over the place. And then here, the one thing to note is that any essential, like any simple closed curve on this surface is going to be homotopic into one of the boundary components. And so really this is just trivial. So we're not going to worry about the pair pants. And so then there's one thing which I'm not going to say more about right now, but is like maybe something you could think about is like what happens for the annulus. Okay, so we'll come back to that, hopefully, if I have time. Okay, cool. Were there any? Oh, great question. So yeah, what is the metric on the curve graph? Just give the edges length 1 and look at the induced metric on the complex. Okay. So, oh yeah, so I'll just write that down, what I just said out loud. Induced metric by letting edges have length 1. Okay, and so some nice facts, like this is a great complex. One of the things is that it has infinite diameter. Another awesome thing is that it's actually a connected complex. I think this could be an exercise. If you feel up to it. Another really handy thing, really important for a lot of GGT people, is that this space is delta hyperbolic. Okay, and so I'm just going to draw a picture of what I mean by that. So what I mean by delta hyperbolic is that whenever I have a triangle in my complex, if you take a delta neighborhood of 2 of the sides, then my third side is contained in the union of those delta neighborhoods. So this is all I'm going to say about delta hyperbolic. I guess the one thing to say is that there exists some delta which works for any triangle in my complex. So I don't want to pick a different one for every single triangle I come across, or you end up with something like you do in Euclidean space, right? Which is not hyperbolic. Okay. So one thing I want to note is that these facts, I can go ahead and write red. These are results of Howie Mazur and Masur-Minsky. So these come as part of the work that they did in those 2 papers that I mentioned at the beginning of the talk. Okay. Awesome. Any other questions? Okay, seems like everything's taken care of in the chat. Okay, so what does this have to do with the mapping class group? What is the best bound for delta? 17. So what does this have to do with the mapping class group? Well, there is a really nice action of the mapping class group on the curve complex. And this is kind of a natural thing to think there would be, because the mapping class group is, right, these homotopy classes of homeomorphisms. The curve class has as vertices homotopy classes of curves. And the great thing about homeomorphisms is that they preserve the intersection number, the geometric intersection number. So in particular, if you have 2 curves which are disjoint, and then you hit your surface with a homeomorphism, then the image of those curves on the homeomorphism are still disjoint. So this is going to preserve edges in the curve complex. Okay, so let me just write down. Oh, let me not be in red anymore. So why does this have something to do with the mapping class group? Well, because the curve complex admits an isometric action so usually I write mod, but I'm trying to use map since I talk about infinite type surfaces now. So sometimes I slip, of map S. And this action is also co-compact, which just means that the quotient of this action is compact. Okay. Awesome. So this has something to do with the mapping class group, at least because we at least know that there's like a fairly nice action of the mapping class group on this complex. Okay, so how does this kind of feed into things? Oh, okay. Maybe I should also write down, since people might want to look at these slides later, maybe I should also write down, I have it in my notes to just write down what I said out loud, which is like, I should really have put these in the other order, but this is a natural action, and it's just from the fact, so I'll just write it for completeness, that homeomorphisms preserve the homotopy classes of curves and the geometric intersection number. Okay. So I said that loud, but just to have it written down. Okay. So in particular, right, this is important because we want disjointness. Okay, cool. Did someone link the Hensel sticky web paper? Okay, awesome. Okay, so why is this a great thing to have? So now I want to kind of zoom out a little bit from the curve complex, like the curve complex in the mapping class group, for just a few slides to kind of illustrate a little bit of a bigger guiding principle in geometric group theory, which we've already seen just in the few talks we've had today. And so the first thing that I want to say about this, so this is the groups acting on spaces. And so there's this very fundamental lemma. So I always say this Milnor-Schwarz, but then it's spelled this way, so I might be pronouncing it wrong. But there's this awesome lemma, which allows us to have a really strong relation between a group and a space when you have a nice enough action of that group on that space. So in particular, if we have a group G.
Marissa, I'm sorry,
Yes.
but there's a question in the chat.
Oh.
Is there a statement about what happens to algebraic intersections?
Algebraic intersection, I think, is also preserved by homeomorphism. I just wanted to be clear because I should have had a slide where I talked about intersections. I just wanted to be clear that I was specifically talking about geometric intersection number, but yeah, that's a great question. Those are also preserved. Okay. So if we have a group G, which is acting by isometries on a proper geodesic metric space, so let's call this space X, and it's acting by, it's acting properly discontinuously. I literally have to spell this word out in my head while I write it, and co-compactly. co-compact. Then we have two really nice statements that we can say. So the first is, then G is finitely generated. So this is always a wonderful thing to have about your group, at least for me. And furthermore, G is quasi-asymmetric. And it's actually stronger than that. You actually get that the orbit maps are going to be quasi-isometries. Okay, so this is good. I'm going to just have as a reminder, because I always forget what properly discontinuous means. Let me just remind us very quickly. It's not a hard thing to say. This just means that for every compact subset K of our space X, that the following, we have this, the following set is going to be finite. So the set, which is just all G and G, which take K not completely off of itself, right? So they don't take K disjoint. This set is going to be finite. So that's just what it means to be properly discontinuous. I feel like I should pause just because this was a long thing of things to write, and I don't want to flip too quickly. But this is a fantastic result to have. This gives us, like, if we can just show that our group acts nicely enough on a space, then we get to transfer so many properties of that space to our group, right? Any sort of property of our space that is a quasi-isometry invariant, for example, like delta hyperbolicity, that's something that is preserved under quasi-isometries. If we can show that our group acts nicely enough on a hyperbolic space, in particular that it acts like by isometries, properly discontinuously, co-compactly, this is often called a geometric action, then we get to transfer those quasi-isometric properties of our space to our group. And so then my natural inclination when I see this, especially after having just listed the properties I did about the curve graph, is to say, does this mean that we can show that the mapping class group is hyperbolic, right? We have the curve complex is hyperbolic, we have a nice action on it, right? And so, sadly, right, let's see. So let me just write down the question I just said out loud. So can we apply Milnor-Schwarz? How did I spell it? Milnor-Schwarz plus Masur-Minsky, right? So we have hyperbolicity of the curve graph from Masur-Minsky. We have Milnor-Schwarz telling us that we can somehow lift some of these properties from a space to a group. Can we do this here, right? We have, I already mentioned a few slides back that we have this nice action of the mapping class group on the curve complex. We have that this action is by isometries, right? We have that this action is co-compact. But as many people probably know, unfortunately, there's a bit of a problem here. And the problem is that this action is not properly discontinuous. Right? So the way that you can see this is that if you look at the stabilizer, of a simple closed curve, it's always going to be infinite, right? We even saw an example of this, right? When you look at the Dane twist, a Dane twist always stabilizes the curve it's twisting about. And so already you have at least one like infinite piece in your stabilizer. So this is always infinite. So we really fail on that properly discontinuous bit. Okay. And in fact, right, you can say, so this shows that Milnor-Schwarz doesn't give you hyperbolicity, but maybe there's some other way. Unfortunately, there are Z2 subgroups. So I put this on my exercise list, is to exhibit a Z2 in the mapping class group. And I've given you all the tools you need to do that just in this talk. And the sad thing is that any group containing a Z2 as a subgroup is not hyperbolic. So unfortunately, despite this hope, we don't have hyperbolicity. Okay, but what about, oh, I left an extra page for me to write more. What about other types of actions that we could look at? Maybe this thing doesn't work out, but there's other things that we could say. Let me shuffle through my notes. Okay, so the next type of recurring theme, again, we're just going to have some sort of action on the space. This one I thought is pretty nifty. So say we have a group G acting co-boundedly. So instead of asking for the quotient to be compact here, I'm just asking for the quotient to have finite diameter. And by isometries, on a metric space X, then again, we have this sort of quasi-isometry popping up. And so this time what we have that X is quasi-isometric to, it's quasi-isometric to a Cayley graph of G with respect to a possibly infinite generating set. So I'm not gonna go into what the Cayley graph is, but it's a kind of very natural graph you can associate to a group. It's a graph that is quasi-symmetric to your group based on the generating set, where you let the vertices be the generators and then you add in edges for your group elements. Possibly infinite. I got that backwards, but okay, we don't need to dwell on what this is. Possible infinite generating set. So the reason that I wanted to mention this one is because this is one that I hadn't thought about until very recently, and one of my collaborators just like mentioned it to me offhand. And the reason I wanted to mention it is because it just gives a very, as a corollary, we have this thing that I just never really thought about, which that the curve complex is a Cayley graph for the mapping class group. I don't know why. This just like, maybe other people know this. Do other people already know this? I didn't know this. So this is just like, so it's just a weird thing. Anyway, so this is a complete aside. This is not relevant for further discussion. But
I don't think I understand the comment. So the curve graph is it's a Cayley graph for the mapping class group.
Oh wait, this can't be true.
Yeah, it's not true.
Because the curve graph is not quasi-symmetric to mapping class group. Okay, so forget this. This is literally just something. So this is a true statement about this. Why?
Is it maybe with respect to some infinite generating set?
It is with respect to an infinite. It's not with the normal generating set.
Yeah.
Oh yeah, that's why. That's why. Yeah, sorry. Sammy, you saved me. It's because normally when we think of Cayley graphs, we're thinking of them for a finite generating set, and that gives you something that's quasi-symmetric to your group. But here, this is telling you that you get a Cayley graph for your group, but not necessarily with a finite generating set. Which is still, it's just a weird thing to think about. These are not even Cayley graphs you would normally think about, but we were thinking about them for something else with like infinite type surfaces. And so it gives you, like, it's just a weird thing that somehow there's this underlying structure in the curve graph in this weird way.
Well, what about the stabilizers? I mean, if you're the Cayley graph, you can't have stabilizers, right? I mean, don't you always act freely on?
So I've never thought about a Cayley graph for the infinite generating set. Right. So that's why I shouldn't have really said this because I haven't thought about it carefully enough. but it's just a weird, I'm pretty sure it's true.
Yeah, okay.
But I think most of the things that you know about the Cayley graph just don't hold anymore when you have an infinite generating set. And so it's not helpful. It's just weird. So sorry for distracting us. I just couldn't help myself. Okay. So like to get back on track, since I've just taken us on a complete derail, I have one last fact, which we are going to relate to the mapping class group in particular, and to say something useful about it. And so this last kind of recurring theme that I want to point out is if, again, we just have some group and it acts, this time we're going to ask for it to act cellularly on a, also if there's questions in the chat, I can see it going like crazy. If there's ones that should be brought to my attention, please let me know. On a connected cell complex. And if we have some subcomplex, whose G translates cover our entire space X, then, so this is giving us not only finite generation like we had with Milnor-Schwarz, but this is going to give us an explicit generating set. Then G is generated by the set G and G, such that G of D intersect D is not of T. Okay.
I'm going to use this tomorrow. Thank you.
Oh, really? Nice. Yeah, see, so these are things that pop up everywhere. And so the reason that I'm mentioning it here is because we want to use this type of action now to show that the mapping class group is finitely generated. Okay.
So a question in the chat is just to make sure that cellularly means that it takes cell to cell.
Exactly. Yes. Yeah. Okay. So now I'm going to state, is this my first like official theorem statement in a talk? I think maybe. So this is a result of Dane and Licorice. And they showed that, yes, indeed, the mapping class group is finitely generated. And it's then generated by Dane twists, which makes me happy. I very much like Dane twists. Okay, and there's some really nice generating sets. So you can write down very nice, very explicit generating sets. So I'm just gonna, there's multiple generating sets for the mapping class group. I'm just gonna write down my favorite, right? And so my favorite set of generators is called the Humphreys generating set. So let me draw my surface. And so this is some surface of genus G, and it's just a very nice collection of curves. So I can literally just write them all down. Okay, I'm literally not literally writing them all down because I did a dot, 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 so I don't need to write them all down. But we just get these kinds of nice non-separating curves like this. And then we add these two extra in here. Just two ones like this. And so this gives the Dane twists about these set of curves give a generating set for the mapping class group. So this is the Humphreys generating set. Okay, so I have about 10 minutes left, yeah. So now I'm just gonna give a sketch of the fact that we have a finite generating set. So it's not really a sketch of this for this Humphreys generating, just that we have a finite generating set for the graphs. Okay. So the first thing that I want to introduce is a new complex of curves. So this, I'm going to denote n hat of s. And this is the non-separating curve graph. Not quite, ish. That's what the hat's for. So what is the ish? So the vertices are what you would hope for them to be. So these are just the homotopy classes of non-separating curves. Of course, these are essential simple non-separating curves. And then the edges, instead of having edges for disjointness, I'm going to say that, so two vertices, A and B, are joined by an edge. If they intersect exactly once. So this is the curve graph. And so here is an exercise. Is that this is, and I think this is not too bad. So SGN, that this is connected. For G2 and N. Okay. So I'm introducing this complex, and we're gonna just look. So this is just a one-dimensional simplicial complex, and we're gonna consider the action of the mapping class group on this. And so the tool, I'm just gonna write it down. It's a little bit technical, but this is basically just a refinement of that kind of last recurring theme that I mentioned earlier. So this is a refinement that we can apply specifically to this situation of the mapping class group acting on this complex. So suppose that a group G so here we're going to act by simplicial automorphism on a connected one-dimensional. So here it really is a graph. Like I'm not having any higher dimensional faces. Simplicial complex. And then suppose. So now we're going to ask for like a bit more specific about the action. So I want G to act transitively. On the vertices. And also transitively on pairs of vertices. Joined by an edge. Okay. And so now let's take two vertices, V and W. So these are two connected by an edge. And I'm going to take now an element in my group such that H takes W to B. Then G is actually generated by H together with the stabilizer of V. Okay. So this is a little bit of a wall of text. I just wanted to include it because I'm not going to go completely into the proof, but with this and the action of the simplex, like the action on the one-dimensional simplex, if you wanted to go totally into the proof, you are equipped to do so. So the idea of the proof then is really simple, right? We take our lemma, we take our action on our non-separating curve graph. And of course, you're going to show some things about this action so that it satisfies the assumptions of our lemma. And then you're just going to sprinkle in a little bit of induction. And the induction is going to be on the genus and the number of punctures. And the base case, I guess this would also be an exercise. The base case is using the fact that the mapping class group of the torus and the mapping class group of the once punctured torus. That looked weird. So that this is generated by just two elements. And they're generated by just the Dane twist here and the Dane twist here. Okay. So I have only a few minutes left and I'm just going to wrap up here. I'm just going to say, like, if you want to see the details, so this last few bits, you can just go to chapter 4 of the primer. But I would encourage you, before you do that, if you do want to do the exercise, I think it's worth first thinking through, like, if you can show on your own that the non-separating curve graph is connected, and think through how you can show what this action on the non-separating curve graph is. You have the tools here. So this is kind of like the answer key, I'd say. So I think it's worth thinking about it a bit before you go and look in the primer. Okay, so I'm going to end there. And just a sneak peek of what's coming up tomorrow is more complexes, of course. There's so many complexes that are naturally associated to a surface, and which the action of the mapping class group on can be very interesting. I'm going to introduce a coarse model of the mapping class group, and then also talk about some of the ways that we can use the curve complex to kind of glean careful and kind of find information about the mapping class group. Okay, so that's it.